Welcome back, listeners, to another exciting episode of Operating Systems Crashcast. I'm Victor, and today we're diving into a fascinating topic in process synchronization: monitors. Sheila, are you ready to explore this powerful synchronization tool?
Absolutely, Victor. I'm excited to unpack monitors for our listeners. It's a crucial concept in operating systems and concurrent programming. Let's start with the basics. What exactly is a monitor?
Great question, Sheila. A monitor is a high-level synchronization construct that encapsulates both data and the procedures that operate on that data. It's designed to provide a more structured and easier-to-use approach to process synchronization compared to lower-level primitives like semaphores.
That's a good introduction, Victor. To help our listeners visualize this, imagine a monitor as a special conference room in an office. Only one person can be in the room at a time, ensuring that the resources inside are accessed exclusively. The room also has a facilitator who manages who can enter and when.
That's an excellent analogy, Sheila. Now let's break down the structure of a monitor. A monitor typically consists of three main components: mutex, which stands for mutual exclusion, condition variables, and procedures or methods that operate on the shared data. The mutex ensures that only one process can execute the monitor procedures at a time.
Right. And this mutual exclusion is automatically enforced by the monitor, which is a significant advantage over semaphores, where the programmer has to implement this manually. Now let's talk about condition variables. These are special variables that allow processes to wait for a specific condition to become true. In our conference room analogy, these would be like waiting areas outside the room.
Exactly. Condition variables support two fundamental operations: wait and signal. When a process calls wait on a condition variable, it's essentially saying, I can't proceed until this condition is met, so I'll wait. The process is then blocked and releases the monitor lock, allowing other processes to enter.
And when a process calls signal on a condition variable, it's notifying that the condition has been met. This wakes up one of the waiting processes, which can then check if it can proceed. It's important to note that signaling doesn't immediately transfer control to the woken process. It just moves it from the waiting queue to the ready queue.
That's a crucial point, Sheila. Now let's discuss how monitors are typically implemented. Most programming languages that support monitors, like Java, with its synchronized keyword, implement them using a combination of mutex locks and condition variables under the hood.
Absolutely, Victor. The monitor ensures that only one process can be active within it at any time. When a process tries to enter a monitor while another is already inside, it's automatically blocked until the monitor becomes available. This automatic blocking and releasing of the lock make monitors easier to use correctly compared to semaphores.
That's right, and it's one of the main advantages of monitors over semaphores. Monitors provide a higher level of abstraction, making it easier for programmers to reason about concurrent code and avoid common pitfalls like deadlocks or race conditions. They encapsulate the synchronization logic, leading to cleaner and more maintainable code.
Excellent point, Victor. It's worth mentioning that while monitors are powerful, they're not without limitations. For instance, some argue that they can lead to less efficient code in certain scenarios compared to fine-grained locking with semaphores. However, the trade-off in terms of ease of use and reduced likelihood of errors often outweighs this concern.
That's a fair assessment, Sheila. Now, let's talk about some practical applications of monitors in operating systems. They're commonly used in scenarios where multiple processes or threads need to coordinate access to shared resources. For example, they might be used to implement a bounded buffer for inter-process communication or to manage access to shared hardware devices.
Absolutely, Victor. In fact, many modern operating systems use monitor-like constructs internally. For instance, the Windows operating system uses critical sections and conditional variables, which behave similarly to monitors, for synchronization in kernel mode code.
That's a great real-world example, Sheila. As we wrap up, let's recap the key points about monitors. They provide automatic mutual exclusion, use condition variables for process coordination, and offer a higher-level abstraction for synchronization compared to semaphores. Their structure helps in writing more robust concurrent code by encapsulating synchronization logic.
Excellent summary, Victor. I'd add that while monitors solve many problems associated with lower-level synchronization primitives, they're not a silver bullet. Developers still need to understand concurrent programming principles to use them effectively. However, for many scenarios, monitors strike a good balance between power and ease of use.
Absolutely right, Sheila. And that brings us to the end of today's episode on monitors. We hope our listeners found this discussion informative and useful. Remember, understanding these concepts is crucial, not just for operating systems, but for any scenario involving concurrent programming.
Indeed, Victor. And to our listeners, if you're preparing for interviews in the field of operating systems or software engineering, make sure you can explain what monitors are, their key components, and their advantages over other synchronization mechanisms. These are common topics in technical interviews.
Great point, Sheila. Thank you all for tuning in to Operating Systems Crashcast. Until next time, keep exploring the fascinating world of operating systems.